Hey everybody, in Honors Pre-Calc. Today we're going to be starting lesson 4.2 on radian and degree measure. So far when we've been looking at angles in right triangles, we've always been using degrees, and we even had to switch our calculator to degree mode from radian mode. Well, today we're going to be starting to talk about the difference between degrees and radians, which are two different units used to measure angles. Just like, feet and centimeters are both different units that we can use to measure length. Radians and degrees are two different units that can measure angles. So what we're going to do, you will recognize and use the vocabulary of angles, and you will convert between degrees and radian measure. The essential question today is, how are radians and degrees related to each other, and how do they help us measure angles? By the end of the lesson, you'll be able to answer a question like this. All right, I'll let you read that on your own if you want, but I'm going to switch over to the notes so we can get started. All right, so here we go. Here are the notes for lesson 4.2, radian and degree measure. We've got all sorts of vocab to talk about today. And today we're going to take angles out of triangles and just talk about what is an angle in general when it's not attached to a specific shape. And when it's not attached to a shape, in our pre-calculus class, where we're going to be studying a lot of trig, we are going to position angles the same way every time on the coordinate plane. So we're going to have our x and our y-axis that we're always going to be looking at when we're measuring angles, and we'll have an initial side and a terminal side of each angle, right? So initial side, you might be able to guess, would be the starting position, initial meaning the beginning, terminal side meaning the end. And the starting position, as you can see here, it's always going to be in the positive x-axis direction. So this right here, I'll try to make it a little thicker, is always the initial side of our angle. And a positive angle is going to go up from there. So potentially it could go to here, and that would be the angle, and this would be considered the terminal side. All right. However, in this lesson, we're also going to be talking about the idea of negative angles, which may be new because in a triangle or another shape, you don't usually think of an angle as possibly being negative. Just like you don't think about a length being negative, but we know that we can have a negative x value. But if an angle is negative, it simply goes from the positive x-axis down instead of up. So we could have a terminal side down here. We can also have an angle that's bigger than 360 degrees, and it just kind of loops around more than once on our shape. So like this terminal side could be the terminal side for this small angle, but also if we went all the way around and then to that angle, that would still be the same terminal side, but it'd be a much bigger angle, right? You'd have to add 360 degrees to the angle. And that is the idea of a coterminal angle, angles that have the same initial and terminal sides. You can either add or subtract 360 degrees and still end up with the same terminal side, same looking angle, but obviously a different value. So that's called coterminal because they end in the same spot, right? They're coterminal. We have complementary and supplementary angles. You might remember this from geometry. A set of complementary angles are two positive angles that add to 90 degrees. Supplementary angles add to 180 degrees. I usually remember the difference thinking that complimenting someone is the right thing to do. So complementary angles add up to 90 degrees, or a right angle. We're also going to talk about angle conversion today. So you might notice already that we've talked about 2 pi, pi over 2 pi in these definitions. And that's where we're comparing radians and degrees. So we would name these angles, first of all. Right here, we have 0 degrees, right? Because that's our initial side. If our initial side and our terminal side were both right here, we'd have an angle that was 0 degrees. If we got to here, we'd have a 90-degree angle. If we got halfway around, we'd have 180 degrees. If we got all the way to down here, we'd have what? 270. And then finally, we'd get back here and we'd be at 360. We got back to where we started, right? Those are the angles in degrees. But we have another unit to measure angles called radians. So I'm going to write a second angle measure at each of these spots. I'd like you to write that as well. So 0 degrees is also known as just 0 radians. And the way that radians work is 1 full circle is 2 pi radians. Now, pi isn't the unit, right? It's 2 pi radians. Pi is a number, 3.14, etc. So when we say 2 pi radians, we mean 2 times 3.14 radians. But since that number is kind of ugly, we don't want to write out a gross decimal. We want to give an exact value. So we usually write the pi in the number. Again, it's not the unit. It's just what we use to abbreviate so that we don't have to write out a long decimal, right? So from 0 to 2 pi radians, that would be 360 degrees all the way around. So halfway around, where we had 180 degrees in radians, that's going to be 1 pi. 1 pi radians. And then if you think about, well, what would half of that be to get to 90 degrees? It would be pi over 2 radians, or half of a pi. And then down here, what would we get? We'd get 1.5 pi, or 3 pi over 2 radians. Let me turn my sound off real quick. I'll be right back. All right, so that's how we can convert, or that's just visually how you can see the difference between degrees and radians. Okay, so 2 pi radians is a full circle. We're going to learn a lot more about degrees and radians in future lessons. But today we are going to learn how to convert, and we're going to use the ratio 180 degrees equals pi radians to convert between radians and degrees when we get there in a couple minutes. We're also going to learn about arc length, linear speed, angular speed, and sector area. Those are all new formulas, all new vocab terms, and we'll talk about that as we get there, all right? But let's just get started here with example 1. Determine a coterminal angle for each angle. The positive angle, 13 pi over 6. So remember, coterminal means if this was our original angle, 13 pi over 6, say, we can either add a full 360 degrees or subtract a full 360 degrees and end up with the same terminal side, which makes it coterminal. The angles have the same terminal side. So it doesn't tell us whether we want to add or subtract, so we can do either. I personally am going to subtract. So if we're starting with 13 pi over 6, I'm going to subtract 2 pi, because 2 pi is the same thing as 360 degrees. And we're going to end up with, again, an angle that ends in the same spot as the original. So then we get, in order to subtract this, I am going to use common denominator. So I'm going to write 2 pi as 12 pi over 6. And then 13 pi minus 12 pi is going to be 1 pi, or just pi, over 6. So pi over 6, or 1/6 of pi, is an angle that ends at the same spot as 13/6 of pi. And that makes sense if you think about it, because 13 over 6 would be 2 pi and an extra pi over 6. It's 12/6, which is 2, plus an extra 6th. And that's going to end at the same spot as pi over 6. All right? So we can do the same thing with letter B. We have 3 pi over 4. We could subtract or add 2 pi. I chose to subtract. And I'm going to look for a common denominator. And let's see, we have 3 minus 8, so that's going to be negative 5 pi over 4. In letter C, now we're starting with a negative angle, but the process is the same. We can add or subtract 2 pi. This time, because we're already negative, I chose to add 2 pi, so the number doesn't get too negative. But that was just a personal preference. You can choose either one. And let's see what we got here. We got negative 2 pi over 3 plus 6 pi over 3 when we find the common denominator. And that's going to give me 4 pi over 3. All right, so those are all coterminal angles with the original that's corresponding in each row. Okay, let's look at example 2, complementary and supplementary angles. So to remind you, we said complementary angles add either to 90 degrees or pi over 2 radians, and supplementary angles either add to 180 degrees or pi radians. Those are equivalent angle measures in different units. So down here, this is probably your first time looking at complementary and supplementary angles with radian measures, but it's the same process, right? So if we had an aside here, if I gave you, 30 degrees and said to find the complement and the supplement, we know we would do, 90 minus 30 would give us 60 degrees as the complementary angle, and 180 minus 30 would give you, what, 150 degrees as a supplementary angle. And that's the same process we're going to use, but instead of using the degrees, we're going to use the radians. So in letter A here, to find the complementary angle, we are going to do 90 degrees, which is pi over 2 minus our original angle. Right, so it's the same idea as in degrees. Now, in order to do this properly, I'm going to change the units, or at least the fractions, so that we have a common denominator. And I'm going to have to use a denominator of 10. So we'll have 5 pi over 10 minus 4 pi over 10. So I get, what, pi over 10? And in radians, we don't usually have to write radians at the end. It's just assumed that that's our unit when we're using radians. So we don't usually even write a unit, and that's acceptable. So for the supplementary angle then, instead of doing 180 minus our angle, we're gonna do pi minus our angle, which means the same thing. I'm gonna find common denominator again. This time I can just do 5 pi over 5 minus 2 pi over 5. So we're going to do 5 minus 2, so we'll get 3 pi over 5. And then that brings us to letter B, 4 pi over 5. So we're going to do the same process again. We start with pi over 2 minus the angle. And for the supplementary angle, we start with pi minus the angle. All right, so I encourage you to try this on your own while I write it out up here. You can pause the video if you'd like. But I'm just going to keep going. So for the letter B here, we're going to have 5 pi over 10 minus 4. Nope, minus 8 pi over 10, which is going to be negative 3 pi over 10. And in the second part here, we've got what, 5 pi over 5 minus 4 pi over 5, which is pi over 5. All right, so we've got an issue with the complementary angle. It's negative. And if you look at the top of our note sheet here, we said that complementary and supplementary angles have to be positive. So this means that our original angle was bigger than 90 degrees. So when we subtracted it from 90 degrees, we got a negative angle. A negative angle doesn't work. So this one has no complementary angle. All right, so that's important to make a note of. And with that, we are going to move on to the back. Example 3, converting between radians and degrees. So I've talked about this a little bit already. Now we're actually going to do the conversion. You kind of saw already how 360 degrees and 2 pi radians both make one complete circle. So let's see if we can convert these between radians and degrees. So if we start with 135 degrees, before we even do that, let's just think about like converting feet to inches, right? If we started with 2 feet and you wanted to change that to inches, common process for unit conversion is multiply by a fraction. And we know that 1 foot is 12 inches. So you usually put the unit you're converting out of in the denominator and the unit that you're converting into in the numerator. And that way, the units that you're getting rid of cancel out. This is kind of in the numerator, this is in the denominator. And then we end up with our answer, which is 24 inches. 2 times 12 divided by 1 is 24. Now that's fairly obvious, right? We should know, hopefully, that 2 feet is 24 inches. But what's not so obvious is what is 135 degrees in radians. But we're going to use the same process. So we start with 135 degrees. We're going to multiply by a fraction. And we know that 180 degrees is half a circle, and pi radians is half a circle. So since we're getting rid of degrees, we put the 180 in the denominator and the pi in the numerator. Just like we had a ratio of 12 inches to 1 foot, we have pi radians to 180 degrees. So we can use this to convert the units. And to calculate this, what I think we should do is on our graphing calculator or on any calculator, we should just type it in, 135. But instead of multiplying by pi, just leave the pi out of the calculator, because the calculator will give us some crazy decimal answer that we don't want. So I'm just going to multiply by 1 over 180, replacing the pi with a 1. We get 3/4. And then in my answer that I write down, I'm going to replace the pi in the numerator. So I'm actually going to have 3 pi over 4. Okay? 135 degrees times pi over 180 is 3 pi over 4. And that's the same thing I'm going to do for B and for C. So I have 540 degrees times pi over 180. If I use the calculator, but exclude the pi, I'm going to end up with 3. 540 divided by 180 is 3. And then I re-put the pi into the final answer. And for the last one here, we have negative 270 degrees times pi over 180. If I type in negative 270 times 1 over 180, I'm going to get negative 3/2. And I replace the pi in the numerator like so. All right, that's how we do that. If we're going to convert from radians back to degrees, it's going to be much the same process. But this time, we're getting rid of the radians, so we put the radian measure in the denominator of our conversion and the degree measure in the numerator, so that the radians will cancel, the degrees will stay. So in letter D here, hopefully you see that the pi's are going to cancel out, so that's going to be really nice. So we're going to have really negative 1/2 times 180 over 1, and we will end up with negative 90, and this is now in degrees, so I'm going to put the little degree symbol. 9 pi over 2. Same idea. We're going to multiply by 180 over pi. Once again, the pi is going to cancel out, and we're going to end up with 810 degrees. And in letter F, now this one's a little different. Take a look. 2 radians. Almost always with radians, you will see that there is a pi factored in to the expression. But sometimes we don't get that, right? So think about that. Pi radians is half a circle, and pi radians is about 3.14. So if we're talking about 2 radians, it's going to be about 2/3 of that. That's what this really means. It's about 2/3 of the way to the half circle. So that's what we're talking about. But we're just going to do the same thing. We're going to do 2 times 180 over pi. But this time, there's no pi over here for that pi to cancel out with, so it's kind of stuck there. So you could say that this is 360 over pi degrees, but degrees isn't usually in terms of pi, so I'm just going to type 360 divided by pi into my calculator so that I get that this is approximately 114.59 degrees. Okay, so that's what we're working with there, and that is about 2/3 of 180 degrees, which is our half circle that we were talking about earlier. So it makes sense that that would be the degree measure there, okay? All right, next up, the rest of the examples have to do with just some formulas that talk about radians or degrees, just applications of this type of a problem. So let's take a look at example 4. This one is arc length. Now, an arc length is the length of a curve if we stretched it out straight. The circumference of a circle is a full circle's worth of arc length. But we can also just talk about, like part of the circle, and that's really what arc length means. So if a circle has a radius of 4 inches, we are trying to find the length of the arc intercepted by a central angle of 240 degrees. Now, we said that half of the circle is 180 degrees. We go down to here, it's 270, so we're talking a little bit less than that. So something like this, that angle is our 240 degrees. And what this question is really looking for is the length from here all the way to here. Okay, so we want to know how long is that curve if we stretched it out straight. And we can figure that out using the arc length formula. So on the front of our notes, we have this formula that says S equals R theta. Remember, theta is an angle, and in this lesson, theta is always measured in radians. So to figure this part out, the question told us that the central angle was 240 degrees. We want that to be in radians. So we're going to multiply by pi over 180. And we will end up with 4 pi over 3. And the question also told us that the radius is 4 inches. So we can plug in 4 times 4 pi over 3. And we're going to get approximately 16.76 when we type that in. And that is a length. And since our radius was in inches, we're working with inches here. So that's going to be in inches, just like the circumference would have been. All right. Now, if we plug in 2 pi for the theta, this formula looks pretty familiar, right? Think about the circumference formula for a circle is 2 pi r. Well, if we plug in 2 pi for our theta, suddenly we have the formula 2 pi r, which is how this is all related and all connected, okay? That's what we're talking about here. So let's keep going. Example 5, linear speed. We're going to talk about 2 versions of speed here, the linear speed and angular speed. Linear speed is the normal version of speed that we always talk about, okay? How fast is something going? Angular speed is how fast is the angle changing. For example, and what we're going to be looking at here is a clock in a second. So if we're talking about the tip of the second hand moving, and we want to know how fast is it moving, that's usually the linear speed, is how fast is the tip of the second hand actually moving. If we were talking about the angular speed, it would be how fast is the angle changing over time from the central center of the circle, right? But let's take a look at this. So the second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of this second hand as it passes around the clock face. All right, so the formula for linear speed from the front of the notes is V equals S over T. And if we take a look at what those variables mean, V is linear speed, S is the length of the arc traveled in time T. All right, so let's think about that. The length of the arc traveled in time T. Well, question doesn't tell us very much. All it tells us is that the second hand is 10.2 centimeters long. But let's think about what we know about a clock. We know that a second hand goes all the way around the circle in 60 seconds, or in 1 minute, right? So we could figure out the circumference of the circle, which is 2 pi r, right? If we do 2 pi times 10.2, that's going to give us the length of the arc all the way around the circle, which is what this S is, right? We said S was arc length. So we have an arc length of 2 pi times 10.2, and it does that in 1 minute. So we're going to plug in 1 for T. All right, so in our question, we were using what, centimeters, and for T, we're using minutes. So we're going to be figuring out how many centimeters does this dude travel in 1 minute, and that's technically a speed. So if we calculate that out, it is approximately 64.09 centimeters per minute. Now, my brain doesn't really know how fast something's moving if it's going 64 centimeters in a minute. So if we wanted to, we could divide by 60, and we would get that we are talking about 1.07 centimeters per second. Okay. So that is an application of linear speed. Now let's talk about angular speed. The blades of a wind turbine are 116 feet long. All right, so we're talking about a pretty big, spinning wind turbine that you might see if you're driving on the turnpike. The propeller rotates at 15 revolutions per minute. Find the angular speed of the propeller in radians per minute. So we want to know how many radians does this thing travel in a minute. And remember, this is not really like how fast is something moving. It's how fast is the angle changing. How fast is it spinning, not how fast is the tip of the blade moving. So we can figure that out if we use the angular speed formula. So back on the front. Now in this formula, we've got a new Greek letter. This is an omega symbol. And we've also got theta, which we know pretty well at this point. But omega here is representing angular speed. It looks kind of like a W. Theta is the angle corresponding to the arc length traveled in time t. And just like before, theta must be in radians. So that we got to make sure we have the radians when we plug this in. Okay, so let's take a look again. So we've got that formula, omega, which looks like this if you write it with a pen or pencil, equals theta over t. And so we got to figure out, if we know it's moving 15 revolutions per minute, how do we plug that in here? So remember, theta is an angle. And if it's moving 15 revolutions, how would we represent 15 revolutions as an angle in terms of radians? And remember that each revolution is 2 pi radians. So we could do 15 times 2 pi, and we would end up with 30 pi. So all we need to do here is 30 pi over 1, because it's moving 30 pi radians in 1 minute. And the question wanted the answer in radians per minute. So we're going to get it. And we can actually just leave it like this. Since it's in radians, we can leave it in terms of pi. So it's going to be 30 pi radians per minute. There we go. All right, letter B, find the linear speed of the tips of the blades. So maybe we also want to know how fast is the tip of the blade actually moving? And we can figure that out. And so we're going to use the same formula that we did up in example 5. And so we need S and T. S is the arc length. So we know that we traveled 30 pi radians, but let's kind of backtrack for a second. S can also be represented as R times theta. So it's going to be the radius, which is 116, times theta. It traveled 30 pi radians. You can also think of that it went around in a circle 15 times. So remember, we did 2 pi for one circle times 15 of those to get this 30 pi. So it's kind of like we're taking a full circumference of the circle times 15. And I'm just going to leave it like that when we plug it in. So we're going to have 116 times 30 pi over, again, a speed or a time of 1 minute. And so we're going to end up with, if we multiply that all out, now this is linear speed, so we don't want it to be in terms of pi. So we're going to actually multiply. And we're going to get 10,932.74 feet per minute. That thing's traveling pretty quick. Okay. All right, last one, example 7, application, area of a sector of a circle. A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. So 120 degrees, if we start with our initial side, is going to be between 90 and 180. So it's going to be something like this. There's our 120 degrees. And we had a radius of 70 feet because that's how far the sprinkler will spray water. So picture this is one of those like sprinklers that turns as it's spraying water. It's probably one of those ones that goes like, you've seen sprinklers like that. And so the sprinkler rotates 120 degrees and then rotates back. So what we're trying to figure out here is this whole area inside of this shape. And we can figure that out using the area of a sector of a circle formula, which is A equals 1/2 r squared theta. And that is coming from the front of the notes once again. And once again, we want theta to be in radians, not in degrees. So we got to start with that 120 degrees multiplied by pi over 180. And we'll get 2 pi over 3. So we're going to end up with 1/2. The radius is 70 squared times 2 pi over 3. And if you type that into your calculator, you're going to get about 5,131.27. And this is an area, and the length of the radius was in feet. So this is going to be in square feet. All right, and just like we did earlier, I want you to think about what would happen if we plugged in 2 pi into this formula as an aside. If we start with 1/2 r squared theta, what if we plug in 2 pi for theta? Well, the 2 and the 1/2 can cancel out, and we're left with pi times r squared. And hopefully that looks familiar to you. That's the area formula for a circle, which makes so much sense, right? Because we're talking about sector area, but if we plug in a full circle, a full 2 pi, or 360 degrees, we should just end up with the area of the whole circle, which is what happens in the formula, right? No matter what r is. Okay, so I know that this notes section is a lot. I'm looking at the worksheet right now, and it is pretty similar to this notes section. So I think you're going to be in pretty good shape here. If I pull this out pretty quick here, in 7 through 10, you're going to try to sketch the angle and state the quadrant in which the terminal side of the angle lies. And remember, quadrants go 1, 2, 3, 4. So figure out what quadrant you're in. If you're on the line, like if you're on one of the angles, you can just say no quadrant. If you're on the x or the y axis, I mean, you can just say no quadrant. And then down here, this always trips some students up. So let me take a look at this real quick. Find the smallest positive and the largest negative angles that are coterminal with the given angle. If the angle is given in degrees, she'll work in degrees. If it's in radians, she'll work in radians, including finding the common denominator. So smallest positive and largest negative. Remember, largest negative means closest to 0, right? If you think about a number line, when you're negative numbers, the closer to 0 you are, it's actually a larger angle. It's actually a larger number. So we're not talking about getting like super, 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 super negative. We're staying close to 0. 70 degrees is smaller than 1 revolution, right? It's smaller than 360. So the smallest positive angle to 70 degrees is going to be if we add 360 degrees to this. The largest negative will be if we subtract 360 degrees from this, because subtracting 360 from 70 is going to get us to the negatives, and that's going to be the negative coterminal angle that's closest to 0. So you're going to have to think like that when you do numbers 12 and 13 as well. I'm not going to give you too much of a hint for those ones, but I bet you can figure it out and you'll have access to the answers. But everything else looks pretty straightforward, I hope. As always, let me know if you have any questions. Thank you so much for watching, and I hope you have a great day.